Welcome back. If you missed part 1, you can click right here to go back to the first part of this discussion. Continuing from part 1, we have now collected our data on the mouse population. So there are 31 mice, 10 of which are albinos. And because the albino phenotype is easily visible in the population, and we know that an albino is homozygous for the recessive allele, with pigmentation being controlled by a pair of alleles, the dominant giving rise to normal pigmentation and the recessive giving rise to no pigmentation or albinism. So each of these 10 mice that are albinos really have the genotype a, and they represent Q squared in this Hardy Weinberg equation. Because the actual population is 31, it means that the frequency of Q squared is 10 out of 31. And this comes to 0.32. So 0.32 equals Q squared, and Q equals the square root of 0.32, which is 0.57. Since we're only considering 2 alleles in the population, then we can say that if Q equals 0.57, then the frequency of the other allele, the big A, is 1 minus 0.57, which comes to 0.43. And now that we have P and Q, we can also find P squared, which is 0.18. What that means is that 18% of this population of 31 are homozygous for the dominant allele. And because 2pq comes to 0.49, it means 49% of this population of 31 are heterozygous. An important aspect of the Hardy-Weinberg equation is the need for random mating. And what we say is that when 2 alleles are brought together in random fertilization, the probability of a Q or a recessive meeting another Q or a recessive is Q times Q, Q squared. And the probability of 2 dominants meeting or 2 P's meeting is P times P, or P squared. And the probability of a dominant and a recessive coming together is P times Q plus another P times Q, 2pq. So this is the basis of the second of the 2 equations. And this first equation is based on this simple case of 2 alleles in a population. Sometimes, of course, 3 alleles can exist at the same gene locus, like in the case of human blood type. Solving a problem when you have 3 alleles in the population is an entirely different issue. But if you want to see a worked example of how to solve such a problem, you can click right here. So these are our current frequencies for P squared, 2pq, and Q squared. And I will see you in 6 months to continue with part 2 of this investigation. As the mouse population continues to change over time, we will return to see if there's any statistical difference in these frequencies, and to answer the question, do we have Hardy-Weinberg equilibrium?